I am a chemist. My PhD work was in fluoride salts, and in particular, lanthanide-doped fluoride salts. So this was kind of a natural progression for me. So the title of my talk is Thorium Nuclear Chemistry. It's a cross-section of nuclear, chemical, and strategic considerations. And I put cross-section in quotes, and hopefully you'll see why relatively quickly. I'm going to talk about thorium fission and resultant products, so this is a bit more of a technical presentation. I give a quick comparison of uranium-235 versus thorium-232 and 233, 235 enrichment, tips and tricks, IAEA monitoring, compliance in 123 agreement, and a little bit about ionium or thorium-230 spiking. There's our thorium-232, brings on a neutron, it transmutes. Protactinium. Protactinium is going to be a bit of a focus for me today because of, as Alice mentioned, proliferation and anti-proliferation are incredibly important on the world stage. And then into uranium-233, and then it becomes fissile. We all know this. I mean, this has been around for 50, 60 years now. It's very well established. The fluorination, as Dr. Seymour pointed out, it's rather trivial to fluorinate all the way to UF6 using HF or another fluorinating compound. These techniques have been refined for decades. Gas neutralization is now computer controlled, and we all learned that from the Stuxnet virus, or I think it was actually a worm that really hit Iran hard. Spent fuel rods are digestic and isotopic segregation, again, as Darrell pointed out. It's also well known. Urex, Purex, tributylphosphate, and trivial due to the different activation energies and oxidation states of plutonium and neptunium. This is just a quick view. So we have calculation, Hartree-Fock versus density functional theory. And then we've got actual XAFs, so it's actual empirical data. So they're pretty darn close. And then we've got Raman and IR down below. And these are inverse centimeters. Okay. The only reason why I put this up is because, and again, we're all looking at the cations, right? So we can compare apples to apples here. We've got uranium, neptunium, and plutonium. And so you see the XAFs. Let's just use empirical data for just a moment. You see the XAFs. The angstrom length is quite similar. So in other words, that means you're inside the crystal, right? Okay, and where the nearest neighbors are with respect to the metal center. Okay, now but the stretch frequency. Look at for uranium versus the Raman and the Raman for the plutonium. Very different. Different enough, whereas these are not even 0.01 angstrom long. That's reflective of the different oxidation states and the different oxidation energies of the valence electrons. This points to the fact that, as Darrell had been saying before, uranium is easier to crash out than plutonium and neptunium. The point of this is protactinium-233 extraction. It's tricky but doable. So why am I focusing on this? Proponents of molten salt reactors, which are thorium-based, quite often say that, oh no, you can't make a bomb. Well, it turns out that in the 50s and 60s, way before I was born, you can. And the fabulous chemists at Oak Ridge and Idaho National Labs who contributed, and Lawrence Livermore figured it out. And you can pull lots of kilos per day out. Why does this matter? Protactinium, you let it sit around for about 27 days, and then it comes back down to uranium-233. It's tricky chemistry. It was done once, way back when, and it's really, really hard. Now, one kind of built-in anti-proliferation feature is the uranium-232 right there. It's a very hard gamma emitter. You need about 30 centimeters of something incredibly dense in order to stop those gammas, right? Very high energy, and they're obviously traveling at the speed of light. Like I said, only 2 U-233 devices were produced, and one failed. The best 233 protactinium liquid extraction requires bismuth in a liquid, a thorium bismuth alloy, and I have the citation down here. And I'm mentioning that for a reason. and I'll get to that in a little bit. Oak Ridge and Hanford authors, that refers to Pacific Northwest National Laboratories in Hanford, Washington. They find that 233 protactinium/233 uranium, a technical challenge and unattractive in comparison to the U-235 plutonium-239 fuel cycle. They said it themselves. They did it, and then they said in the report, don't do this. It's really hard. And it's a hell of a lot easier to do centrifugation. We want to ensure basically zero possibility for proliferation. Zero. And as Darryl pointed out, we're chemists, so we can think about what goes in and think about what comes out. If you start, just high school chemistry, if you start with a fixed number of moles on the left side of your arrow, you're going to get a fixed number of moles of whatever your products are on the right-hand side of the arrow. And that matters a lot to chemists. That matters a lot. So with a fixed reactor size, fluorination is a fixed molar mass. With a fixed reactor size, fission products are also molar quantities. Here's a big one. Fluorinating compounds can be isotopically tagged. And I'll get to that in just a second, because I have just one example, but you can do lots of examples. Salt handling cradle to grave is easily monitored. Moles are moles. So if somebody's going to try and port off 10, 20, 50, 1,000 kilos, you know something's going to be missing. Because we're chemists. We know on the left-hand side of the equation, you got to add it up to the right-hand side of the equation. So vitrification, and Darryl's a world expert on this, or composting, plutonium-239 masses are chemically meaningless in a molten salt reactor because they're so small. They're almost zero. Neptunium-237, as far as a country, any nation state that's working on this is concerned, is ridiculously valuable. You can power lots of RTG batteries with plutonium-238. Here's another anti-proliferation measure. How about measuring thorium-228 moles periodically? The decay rates are known, and starting with known fuel load yields moles of thorium-228. Here's another interesting idea, which is also a pretty neat one. So why don't we spike it with thorium-230? Okay, the old name of thorium-230 is ionium. Okay, so we can distill this. Somebody mentioned Ontario before. Well, there's lots of this in the tailings just outside Ontario, just northwest of the city. Okay, lots of it, because there's lots of uranium tailings there. Okay, so it's about 17.4 grams per metric ton of uranium total. It contaminates protactinium-233 load. Okay, so, and I put this here, and I put the half-lives very specifically. They're really short. Okay, so you can build the molar ratios of these, and you could probably go 232 protactinium divided by 231 thorium. Wow, and you can keep a ratio going. Okay, so you can get near real-time evaluation and monitoring the spiking. MSRs are chemical plants, so you really care about what's on the right-hand side of the equation. So again, these are nation states where we live in an international world. Okay, the IAEA and the 123 agreement signatories are basically the purview of the NNSA here in the United States for the 123. International monitoring protocols are already established. We know that. They've been around for a long time. So we have to trust but verify, even though I don't like the guy who said that. The take-home messages. The 232 fuel cycles are overall safer for civilian use because of the greater distance, if you will, all the way up to plutonium-239. The high energy density, as many people have already covered here, of modular reactors, that facilitates dramatic increases in nation-state electricity production. And it also provides an excellent high-heat platform for high-temperature chemistry. That's incredibly important. I point out one process, the Bosch-Haber process for making ammonia. You need a lot of heat to make nitrogen a Lewis acid. In other words, take on those protons to make NH3. That's really hard, and so far it's basically, by and large, completely thermally driven. Wow. At an operating temperature of 650 Celsius, while I'm not thrilled about the use of fertilizers, in developing countries, you can feed all the people. And that's just one example. I can give you 30 examples of high temperature chemistry that occurs. I'll give you another example. For every degree drop in sodium zeolite Y matrix bed chemistry on the part of ExxonMobil, you guys have heard of ExxonMobil, they consider it $50 million increase in their bottom line. For every degree Celsius. Why? Because they're right now operating at around 300 degrees Celsius to make pretty much all of the precursors for all of the very nice plastics and polymers that we use all the time. It's in this room right now. It's in that projector. It's in my laptop. It's in your cell phones. That's remarkable. So this would actually bolster the GDP of countries. I mean, that's pretty remarkable. And do so with safe, somebody said before, better living through chemistry. Well, it's true. It's true. Protactinium chemistry is a distinct possibility. Offloading, you find a rogue nation, you find a boatload of molten salt chemists. I say that kind of tongue-in-cheek because I don't know anybody my age who is a salt chemist. I really don't. So all of that technical know-how, all of those skill sets are effectively gone. You look at the authors of the papers that I listed, most of them are deceased. Grimes, Rainey, they're deceased. All that technical skill is gone. And I'm reading ORNL documents fiendishly to try and go, okay, I think I haven't did that. I think I haven't did that. But I don't know. I don't know because I don't have anybody to talk to. So I'll reiterate, it's unattractive given historical technical testimony by American scientists. They all said, okay, we can do it, we can pull it off, but it's really, really hard. It's also unrealistic, given the theoretical reliance on bleeder blanket reactors. In most of the literature cited here, almost everyone was saying breeder. But technologically speaking, what is neutron invisible and is also chemically resistant to these ridiculous environments, and not going to fail pretty quickly because of transmutation into other daughter nuclides within the wall itself? Now that's a technical challenge. Hastelloyen is a pretty good candidate, but it's not great. Not a lot of people talk about the chemistry, either solid state or liquid. And these are very real things. So by and large, if you can come up with a breeder blanket with a wall, which to my knowledge you can't, that can be removable and throw it away.
That's the key, right?
Right, that's the key. How do you do that?
Well, that's why we need to allow the engineers to think about it.
Absolutely.
Right.
And chemical engineers, no less. I mean, you can come up with ways of doing that, but my God. Go out and buy a gas centrifuge from the Iranians who got sold the technology from the people who were dealing in Switzerland. I mean, we read it in the New York Times, we read it in the Washington Post. It's already out there. You can download it. Hell, I can download a neutron gun from the French website. So, and I speak French, so it's pretty easy to do this. This is really, really hard, okay? The non-zero threat of protactinium must still nevertheless be made known, okay? But here's the interesting thing. Again, I'm a chemist. The reagents needed are rather easy to restrict. So let's talk about that. Like I said before, fixed reactor sizes mean fixed moles of product. So just measure it. No breeders permitted, mostly because you can't build one. And tube fluid currently is not technically feasible. Here's the most important part. I referred to the protactinium extraction using a fluid extraction method, okay? Some pretty fabulously smart chemists back in 1956 used the liquid extraction method for bismuth and thorium. And they did so using really clever chemistry because that's a Lewis acid-based system. So everybody go back and start studying how clever Lewis acid-based systems in this particular case were. They were able to crash that out. But guess what? Bismuth is pretty rare. surprisingly, and it's restricted to certain countries. So if you control bismuth, you don't really have to worry about protactinium. We can offer a denatured MSR as an option. Denatured MSR, and then do combinations of these anti-proliferation measures that I'm suggesting here. How about encourage more 1-2-3 agreement membership? We have a lot of signatories on that agreement, but we don't have all of them. We can also think about satellite-based monitoring of gamma emitter movement. If you're really worried, 232 is pretty hot. And you can see that from space. That technology's been around for 20 years. So we can track and control fluorinating compounds. For you guys who don't know, iodine is a solid at room temperature. It's easily transportable. And you have a unique and completely pure isotopically tagged isotope. You go fluorinate it off-site, and you bring it back. Because you're going to have to keep fluorinating, right? We're chemists, so we have to keep fluorinating because you're making fission products. The oxidation states don't match up, so occasionally you're going to have to keep fluorinating. Okay? Well, this is an outstanding fluorinating agent. It's been known for decades. So this is a pretty neat idea. Look at this. Hit it with a neutron, and it goes to xenon-130. Well, xenon-130 has almost zero neutronic cross-section because it spins zero. I'm trained in nuclear magnetic resonance, so I always use the kets, the Dirac kets here, to give a rough idea to the audience as to whether it's a big neutronic cross-section or a small one, because there's a rough correlation between the two. Xenon-130 is highly valuable. If you're developing this in a nation state, wow, they can go sell it. Oh, and wait a second. Under these conditions, you can't form xenon tetrafluoride, so it's just going to bubble out. Great, even easier, because it's an elemental at that point. Iodine-129 is a pretty massive neutronic cross-section, so it's probably going to get hit with a neutron. Look at the size of that thing. It's 30.6 barn. That's massive. The most stable isotope of iodine, which is a bear for me to do in magic angle spinning nuclear magnetic resonance, and I did that in my PhD work, is only 731 millibarn. So that's a massive difference between the two. You make ionium spiking mandatory. That's pretty easy to do. You can spike the fuel before you send it. Right? You can monitor anything you want. You can monitor iodine-129 coming off. You can monitor the krypton coming off. And the krypton is a poison, so they want it out anyway, a neutron poison. So all of this can be monitored with teeny tiny sensors that are, for example, behind beryllium oxide windows, and so which makes the sensors easy. And then encrypted satellite transmission. And we're getting close to quantum transmission, so it'll be unbreakable. We're getting very, very close to that. So there's your encryption. And you can monitor this using UV, Vis, XRF of all MSR compounds in situ. This was proven in 2011, and the citations are unfortunately at the bottom of the screen. And this is, so you may want to ask, for example, hey, wait a second. This boils at 43 Celsius. Well, so what? You carry it around. You ship it in a refrigerated isotainer, for example, which are shipped all over the world. Great, it decomposes instantly. So you're potentially actually adding more value into your mix because you're going to make xenon-130. Now it instantly decomposes into a fabulous, so you can use this as a fabulous fluorinating agent. So that's it. I have some grateful acknowledgments to Ed File for some fabulous discussions. He just gets up really early. 5 o'clock in the morning, start talking about nuclear physics and chemistry. It's very difficult to do. Bruce Hobbins for some fabulous ideas. He's the one who actually promoted the ionium spiking. And Dr. Alex Canera for putting this all together. You can tag whatever the heck you want. You can monitor stuff on the back end. And I remind everybody, these are chemical plants, and we're chemists, so we measure the moles. We measure the moles. So there are many, many, many things that you can do to basically eliminate what is perceived as a threat, which is the protactinium-233. I would argue that it's not. I would argue that it's not in any way, shape, or form, because with a little bit of cooperation, which we already have infrastructurally, right? We already have the IAEA, they're based out of Vienna. We already have UN monitoring in place. So this is very simple stuff relative to trying to monitor where the 235 goes. They already found it in Iran in the supposedly secret processing facility. They found 28% enrichment lying around. That's not good. So there you go. That's it.